I think we talked about these ideas earlier in the year, but when we're sketching polynomials, things to look out for. We know that the constant will always be the y-intercept, because if you sub 0 in, all the terms with x will disappear and you'll just be left with a constant. So my example for this one, and again, you don't have to expand the whole thing out, because we know the constant will always be the constant times the constant times the constant. So we're going to have 1 times -1 cubed times 2 squared, which is negative, isn't it? Yes, -4. So no, -4. Plot that in. We know the x-intercepts are the roots or the solutions to the equation. Now, fortunately, my one's been factorised already, so we know we'll have it at -1, +1, and -2. As x approaches plus or minus infinity, polynomial x acts like the leading term. This is all to do with something called dominance. As x gets bigger and bigger and bigger, which term will dominate? And it's always going to be the leading term because it's going to have the highest power. So it's the one that's going to get bigger the quickest. And so and that's why all we got to do is look at the leading term to determine, well, where's this polynomial going to start? Where's it going to finish? I don't actually have to look at the whole polynomial itself. So when I look at this one, we've got x times x cubed times x squared. That gives us x to the power of, what are we up to there? 6. If I was to just draw x to the power of 6, I know it would start up there and it'll finish up there. So our polynomial will do the same thing. Multiple roots, when we're at those x-intercepts, if the root is an even power, then it will touch it like the power, so it'll have a U shape. The bigger the number, then as it touches it, the shallower at the base, the steeper at the sides. So on ours, at -2, now I know it starts up here, so it must come down and turn like a parabola at -2. And odd powered ones will inflect like the cubic does. But again, depending on the power, the higher the power, then the shallower at the base, the steeper at the sides. Our one's the power of 3, and that's at +1, but I know I've got to finish up there, so it must come through like that. -1, well, it's a linear function, x plus 1, so it'll just cut through like a straight line. I also know that it'll cut the y-intercept. If I wanted to, I could use calculus to find the turning point, to see whether it turns before the -4 or after the -4. But in this one, it actually turns out it turns before -4. Now, if you can factorise it completely, then I know it's just, we use our shifting ideas. So it's x minus a to the power of n, it's the basic curve of x to the power of n, but just shifted horizontally a units. Alright, let's do another one. So I've got x minus 1 to the 4, x plus 1 cubed, x plus 2 squared, x minus 2. We know that the constant on this one's going to be -1 to the power of 4, that's +1. 1 cubed, that's also +1. 2 squared, so we're up to 4, -2. We know that's at -8. It's going to start and finish like x to the 4 times x cubed, so that's x7, x squared. We're up to x to the power of 9, times it by x, we're at x to the power of 10, so it'll be like the last one we looked, it's going to start at the top, finish at the top. What else can we tell from there? We know our x-intercepts. This one's going to look like a quartic at 1, it's going to look like a cubic at -1, it's going to look like a parabola at -2, and it's going to look like a straight line at 2. I think that's probably enough. Let's put it all together and we'll see, yes indeed, that's what our graph has turned out like. So you'll notice over here at +1, you see compared to the one at -2, how it's flatter and a little bit steeper at the sides when it gets bigger. Lovely. And again, if you wanted to find out exactly where those turning points were, you can go and use your calculus and find stationary points and things like that. Alright, that'll do us.